Welcome back to The Explainer. Today, we're going to decode something that is honestly the most misunderstood, but absolutely vital fluid on a deepwater drill ship. You know, when most people think of offshore drilling, they picture massive steel derricks, complex robotics, giant thrusters, all the heavy metal. But today, we're looking at the true lifeblood of the operation, the fluid that physically makes drilling possible in the first place. So let's just dive right into this. If I were to ask you to name the absolutely most important safety system on a drill ship, your mind probably jumps straight to, I don't know, a giant mechanical valve, or maybe a screeching ship-wide alarm system, right? Well, I want you to completely rethink those assumptions, because as we're going to see today, the ultimate safety system on a drill ship isn't a mechanical alarm at all. It's actually the mud itself. Listen, we really need to shatter this illusion right now that drilling mud is just, well, some slurry of dirt and water. This is a highly engineered, precisely mixed chemical fluid, and it's doing 5 massive jobs all at the exact same time. It controls the downhole pressure, essentially holding the ocean and the earth at bay. It acts as this liquid conveyor belt, constantly carrying rock cuttings to the surface. It cools the drill bit, which, by the way, would literally burn up from friction if it didn't. It lubricates the entire drill string. And finally, it stabilizes the wellbore wall. It does this by physically baking a filter cake, plastering the porous rock right at the sand face to keep the whole hole from just collapsing in on itself. Section 1. The mud circulation loop. Okay, to really grasp how it pulls off all 5 of those jobs simultaneously, we have to track the actual physical journey of a single drop of this mud. And it's a continuous cycle. First off, high-pressure pumps force the mud all the way down the inside of the drill string. Second, it blasts out through the nozzles in the drill bit at the very bottom of the ocean floor. Third, it pulls a U-turn and returns back up the annulus, which is just the gap between the drill pipe and the hole. Fourth, it arrives back at the surface where it has to be aggressively cleaned. And fifth, it's dropped right back into the active pits to be pumped down again. The drill ship maintains 14 of these active and reserve pits just to keep this process looping infinitely, without ever stopping. To ground all this technical stuff into some harsh sensory reality, when that mud returns from the depths, it comes into a room called the shaker house. And offshore geologists from our sources described this room perfectly. They said, it's really dirty, very, very noisy, and very, very smelly. And of course it is. It's full of pulverized rock and subterranean gases that have just been dragged up from thousands of feet below the seabed. Section 2. The drill ship's dialysis machine. That smelly, noisy room, that is the start of a seriously critical cleaning phase. To understand exactly how the ship processes this incredibly dirty, gas-filled fluid, think about how human dialysis works. Blood leaves the body, toxins are removed, and the clean blood returns in a continuous loop. Well, our mud processing system functions exactly like a massive medical dialysis machine. The drill ship constantly cleans the fluid, removes dangerous gases and solid rock, and returns it seamlessly via those 14 active pits. It's keeping the well alive by constantly maintaining perfect fluid chemistry. So, the primary kidneys in this whole operation are the shale shakers and the degassers. The shale shakers violently vibrate the returning mud across screens to strip out the solid rock cuttings, kind of like a giant sieve. Then, the degassers act as vacuum units to pull out any trapped hazardous gases. This is actually exactly where the offshore geologists do their work. They wait for exactly 1 lag time, which is just the time it takes for cuttings to travel from the bit up to the surface, and then they collect rock samples directly off these vibrating screens to analyze exactly what kind of rock they're drilling through under a microscope. But, you know, that shaker room, it's inherently dangerous, because this is the exact spot where the mud releases whatever it absorbed down below. These shale shakers are fitted with safety-critical fume hoods. Operating these shakers with damaged or bypassed fume hoods is a direct gas exposure hazard to the personnel. Hydrocarbon vapors and highly toxic, sour H2S gas can break out of the fluid right here. In fact, this area is so high risk that it's linked directly to the ship's automated fire and gas detection sensors, ready to trigger emergency shutdowns if the gas concentrations get too high. Okay, so once the rock and the gas are completely out, the crew has to continuously adjust the mud's chemistry. They are actively tweaking its density, its viscosity, its wetting ability. And to do this, they use a pneumatic bulk transfer system to blast dry materials, we're talking barite, cement, and bentonite, directly into the mixing system. They're constantly altering the fluid to match the ever-changing conditions thousands of feet below the seabed. Section 3. heavy-duty pumping power. Now, once that mud is perfectly cleaned and perfectly mixed, it requires just a staggering amount of mechanical muscle to push it thousands of feet down a very narrow pipe. Enter the triplex mud pumps. These are massive, 3-cylinder positive displacement pumps. A drill ship like the GF-12000 uses 4 of these N14 P220 models. Every single one of these pumps brings 2,200 horsepower to the table. And what's really amazing is that they're driven by AC motors that make the flow rates infinitely controllable. So you can have the pumps just gently ticking over, or you can have them aggressively pumping 200 strokes per minute, depending on exactly what the well demands. And if you want to figure out the rig's total capabilities, you use a pretty simple formula. Total installed pump power equals the number of pumps multiplied by the horsepower per pump. So doing that math, 4 pumps times 2,200, you get 8,800 total installed horsepower. To put that massive figure into perspective, that is literally the equivalent of taking the combined engines of about 7 heavy-duty diesel semi-trucks and dedicating 100% of their power entirely to moving mud through one single well. Section 4. The first line of defense. So all of this power and all of this relentless cleaning leads us to our final extremely high-stakes realization, why the mud's weight is actually a matter of life and death. The crucial point here is hydrostatic pressure balance. Deep down in the earth, porous rocks are full of water, gas, or oil under immense natural pressure. To stop that pressurized fluid from just exploding up the wellbore, the crew engineers the mud to be heavy enough that its downward hydrostatic pressure slightly exceeds the upward natural formation pressure. If that balance fails, you get an uncontrolled influx of fluid into the well, which is known as a kick. So you see, mud weight isn't just some passive housekeeping metric. Even the absolute smallest deviation is a severe, critical well control indicator. When we actually contrast the two ultimate barriers, the stakes become crystal clear. Yes, you have the blowout preventer, the BOP, a massive, hard, static, mechanical barrier sitting on the seafloor. But before that, you have the drilling mud. The mud is the primary dynamic pressure balancing barrier. It's actively fighting back against the subterranean pressure minute by minute. The entire goal of this massive mud processing system is to keep the well perfectly balanced so that the mechanical BOP never even has to activate in the first place. Which leaves us with one final, pretty provocative question. We've seen how the mud acts as the ship's continuous dialysis machine, holding the explosive pressures of the earth safely at bay. But what happens if that fluid gets too light? What happens if that continuous loop is broken or the hydrostatic pressure balance entirely fails? Because when the fluid that does absolutely everything finally meets a pressure it just can't hold back, the vessel has only seconds to rely on its very last line of mechanical defense. And that is the topic for our next explainer.